Now we're going to look at one of the basic theorems regarding planar graphs, which is Euler's identity, that says if you have a connected plane graph of order n, size m, and r regions, then n minus m plus r equals 2. So the reason it says plane here rather than planar is because we have to think about how it's drawn to be able to identify how many regions it has. So if we look at, say, K4, for example, we have n vertices, m edges, and 1, 2, 3, 4 regions. And we can verify that n minus m plus r does equal 2. And another simple example would be K23, which has 5 vertices, 6 edges, and 1, 2, 3 regions. And again, 5 minus 6 plus 3 does equal 2, so that is verified. So if we wanted to prove this, we could think about two cases. The first would be that we think about our graph G being a tree. So trees are always planar graphs. They can always be drawn in the plane, and they always have one region. So if G is a tree, then R will equal 1, always. So if we think about the number of vertices minus the number of edges plus R, that's going to be n minus m plus 1. And of course, with a tree, the number of edges is always 1 less than the number of vertices. So the substitution there will give us n minus m plus r being equal to 2. So definitely works for trees. Now, if we move on to, G is not a tree, well, it's a connected graph and it's not a tree, so we know that n needs to be at least 3. So if you're not a tree and you have 3 vertices, well, there's only one option. So we'll think about if n equals 3, G is just going to be isomorphic to a cycle of length 3. And that's obviously planar. So that's the only option we have. And if we think about C3, the number of vertices is 3, the number of edges is 3, and the number of regions is 2. So n minus m plus r is equal to 2. So that definitely works. So it works for n equals 3, and the reason I kind of separated out that case is because the rest we can prove by induction. So what we have here is the base case for induction. Okay, so here's our setup for proof by induction, and the proof by induction is actually on the number of edges. So the base case of C3, we'll think of that being the base case where the size equals 3, so m equals 3. And of course, if you had fewer than 3 edges, your graph would have to be a tree if it's connected. All right, so base case m equals 3, and then we're going to have our induction hypothesis. Suppose any plane graph with k edges satisfies Euler identity where k is at least 3, so at least our base case. And then we think about a plane graph with k plus 1 edges. Now remember, this is the non-tree case, so that means our graph must have a cycle. So what you're going to do is you're going to find a cycle of G, and we'll identify an edge on that cycle. And we're going to let E be an edge on that cycle. Then we're going to remove an edge from E. And what happens if we remove an edge from a plane graph? Well, it's still a plane graph. If G was drawn without any edges crossing, then deleting an edge doesn't change the planarity. So G minus E is a plane graph. Now, what happens because the edge was on a cycle is that whenever you delete an edge that's on a cycle, you are going to join two different regions. So for example, what if I thought about deleting that particular edge? Well, this region and the outside region would be opened up and become a single region. And the same would happen for any cycle because every edge on a cycle borders exactly two regions. That's not true of an edge if it's not on a cycle. So for example, if I look at this bridge, if I deleted that bridge, I would just, still be joining the exterior region with the exterior region. You're not going to create kind of a new, bigger region. But if I look at any edge on the cycle, I'm either going to, have an edge that's going to take two kind of interior regions like R1 and maybe this region and open those up, or open up an interior region to the exterior region. So that always happens when I choose an edge on a cycle. So what happens is this is a plane graph. It has the same number of vertices as the original graph, and it has one less edge, and it has one less region. So let's say that this graph G minus E has n prime vertices, it has k edges, and it has r prime regions. And because of my induction hypothesis, this plane graph satisfies Euler's identity. So the number of vertices minus the number of edges plus the number of regions equals 2. That's by the induction hypothesis. All right, so now I think about what's happening in G. G has, well, n prime vertices. And I've just written m prime, just not to confuse it with kind of the general n here. It has k plus 1 edges, and it has r prime plus 1 regions. Because when I deleted that edge from G, I decreased the number of regions because I combined two regions into one. All right, so then if I look at the number of vertices of G minus the number of edges of G plus the number of regions of G. So looking at the left-hand side of the equation for G, well, I'm going to get n prime minus k plus r prime, and then I would have minus 1 plus 1, so those ones disappear, and I'm left with this, which I know is equal to 2. So Euler's identity works for G. So therefore, by the principle of mathematical induction, it works for all of them. So it all hinges on that when you go from G down to G minus E, you've deleted an edge, but you've also reduced the number of regions. So both your size and your number of regions go down, and because we're subtracting edges and adding regions, the value of that left-hand side of the equation hasn't changed.